Welcome to Chapter 6, the chapter on GPUs or graphics processors. So here is the background that we require for this chapter. So we need three things specifically. We need in-order pipelines, a basic knowledge of C++ programming, and some knowledge of parallel programming. So for parallel programming, you can also look at Chapter 9. That will give you some idea of parallel programming or the first part of the two-book series, Computer Organization and Architecture. So that has something about parallel programming, or you can consult the web or any other book. So broadly speaking, from this book, we need Chapter 2 and these two as a matter of backup. Nothing else is required. So there are three parts to this chapter, three sections. First, we'll give a broad overview of application-specific computing, notably existing GPUs, ASICs, and FPGAs. Then we will look at the CUDA 10 programming language. So even though as we speak, CUDA 11 is the latest, but we'll discuss CUDA 10 because that for us is complex enough. And also at the time of writing this book, it was the latest version. And finally, we'll go to the design of GPGPUs. So let's first start with the question, are we satisfied with an IPC of 4 or 6? Even achieving this IPC is quite hard. So if you look at a very aggressive out-of-order processor with all the tricks that we have done. So with all the tricks with regards to advanced speculation, replay, pipeline optimizations, all of that, including memory system optimizations, getting an IPC of 4 or 6 is very hard. Right? So the typical IPC for an out-of-order pipeline, even if it's 4 issue, would be between 1.5 and 2.5, typical. So even getting 4 or 6 is quite hard, almost impractical. But it turns out that we are not satisfied with it. The reason being that if we consider very large programs, such as, for example, simulating an airplane wing, weather prediction, image recognition, they have far more, they have far serious ILP requirements and far higher performance requirements as well. So the reason I say that is because linear algebra, particularly matrix algebra, forms a core of these methods. And consequently, if let's say I were to add two matrices, then the instruction level parallelism is huge. And in that, an IPC of 4 or 6 is actually too low. So you consider this piece of code. So in this piece of code, we're just adding two matrices element by element. So if you look at this, then we have two loops iterating from 0 to n, loop iterators being I and j. So if you consider this, then what we can see is that for different pixels, these are completely independent computations, totally independent. Okay. So for different pixels, these computations are totally independent. So for large values of n, we have truckloads of parallelism. We have a huge amount of parallelism, right? If n is a large value. The reason is we consider n square points, and all n square points can be processed in parallel. All of these order n square additions can happen in parallel. And that is exactly why we are not satisfied with the meager IPC that we get. We need a different computing platform. So what's the main big deal with these high-ILP programs? Well, many of these linear algebra based programs that deal with matrices, regardless of the matrix operation, they have a very high degree of ILP, extremely high degree of ILP. Existing multi-core processors, such as the ones that we have designed, possibly maybe with one or multiple out-of-order cores, they are very general purpose in the sense they are designed to execute a very large array of programs. So they are kind of constrained by their fetch and issue width, which is not much. It is limited to 4 to 6, and that also restrains the IPC to remain within this value. So a solution here is to create a new processor that has hundreds of ALUs. So what we want to do is that we want to design a different kind of processor where we will have very, very small computing units, right? Hundreds of small computing units Okay, so we'll have hundreds of small computing units. And what these small computing units will basically give us is that, let's say for these simple pieces of codes where we have to do many additions or multiplications in parallel, we'll be able to realize a massive amount of parallelism. So for these small computing units, we can either call them an ALU or a core. They're often small 1 to 3 issue in order cores. They have a very simple ISA. Many of the advanced features of modern programming languages, such as irregular memory accesses or conditional branches, are not supported. So what we need to do is we need to create a processing framework for such kind of parallel programs that have a massive number of parallel yet simple operations. So the key point is that the operations are simple. So we'll now discuss ASICs, ASIPs, and FPGAs. So what we want to do is we want to create a custom chip with hundreds of ALUs. So one of the options is to create an ASIC, an application-specific integrated circuit. So this is done only for a specific application, specific kind of application with the inputs, outputs, formats, everything is fixed. So instead of using software, we just create a chip for it. But needless to say, there has to be a market for it, because without a market, we cannot really design a chip. So this will be used in all kinds of devices, which include, well, let's say that ASICs are used in all kinds of devices, but it doesn't mean that the same ASIC is used in all kinds of devices. Different ASICs are used. For example, let's say for a video camera, they would have to do image processing at a very fast rate. So we can have an image processing ASIC with it. For washing machines, we'll require a different kind of chip. So we will fabricate a different ASIC. And given the fact that video cameras and washing machines have a huge market, what we can do is that, well, we have a large enough market to justify the creation of a specific chip for doing a specific task. So these are in general not all that programmable. So as I said, ASICs have a lot of value in the sense that we need not have large processors that run programs, but they have a lot of value in specific scenarios. They can be made more programmable if we move from ASIC to ASIP. An ASIP is an application-specific instruction set processor, which brings in a little bit more in terms of flexibility. So it provides a degree of flexibility in the sense there is some ISA support. So you can think of it as a weak processor with very heavy ASIC-like functionalities. There is a basic ISA support, and there is definitely some flexibility, including the flexibility to write small programs. But of course, what you can do is quite limited in that. Then we have PLAs. So in the good old days, we had programmable logic arrays or PLAs. So if you look at it, this can be used to implement any Boolean function. So for example, if let's say we have three inputs, A, B, and C, then the inputs at this point will become A bar, B bar, and C bar. So here the idea basically was that we choose a subset of these. So clearly we can't choose A and A bar both together, but we choose a subset of this, for example, A bar, B, and C. So what you're seeing in this wire, so this is not a single wire, but it is actually a group of 3 wires that are going into this AND gate. So the first wire is carrying any one of A or A bar, the second one any one of B or B bar, and the third one any one of C and C bar. So essentially the AND gate over here is computing a min term. So that is why this is known as the AND plane. So just to remind you once again, this is not a single wire, but a set of 3 wires. So here what we are doing is we are computing the min term. Okay. And so the advantage of computing the min term over here is that we can compute different kinds of min terms. So let's say we want to, let's say, compute ABC. Our function is of this type. Then the first min term could be ABC. The second one could be A bar, B, and C bar. Then what we can do is we can take two wires like this, and we can leave the rest, so it doesn't matter. So we can choose in for this vertical wire. Again, we don't have a single wire, but let's say we have multiple wires. So we have 8 wires. So out of this, we can only choose these two and send them to an OR gate. So then the output over here would basically be the output of this sum of these two minterms. So similarly, we have other OR gates. So this is known as the OR plane. So they can then take another set of minterms and maybe like enable them, enable this, this, and this, and compute OR of this. So this will be another Boolean function. So this is being used to compute Boolean functions. So we are computing F1, F2, F3, and F4. So in this case, as you can see, we can generate 1, 2, 3, 4, 5, 6, 7, 8. We can generate 8 minterms. Okay. And then among the 8 minterms, what we can do is that we are generating 4 functions. So we can choose any of those 8 minterms, do an OR, a logical OR of them, and we can generate 4 Boolean functions similar to the way that they are generated. So as you can see that these selecting units over here are fully programmable. That's the reason we call this a programmable logic array. Where given a Boolean function and a set of variables, we can implement it. In fact, we can compute several Boolean functions together. So that's the reason even implementing something like an adder can actually be quite simple, because one of them could be the Boolean function for the sum and the other one for the carry. So this, as you can see, is a quite flexible programmable logic array. This, of course, PLAs have been superseded by FPGAs, because PLA is only for combinational logic functions. There are no state elements. But to implement something similar to a processor, we need state elements, in the sense elements like flip-flops and registers which can store values. Right? So we need some sort of a bit storage mechanism, something similar to a state element. And we need a flexible interconnect, right? So basically, why a flexible interconnect? Because we'll have to store different logic elements, connect different logic elements to different state elements. And that is where we have the opportunity of creating a custom processing unit. So this is why we use an FPGA which has these things. So you can think of an FPGA as an extension of a PLA that has state elements and the flexibility of connection. So what it does is that, along with programmable logic, so incidentally now the amount of programmable logic in FPGAs has gone down quite substantially. So given that the presence of PLAs in FPGAs has reduced quite substantially, we have moved to lookup tables or LUTs. So here the idea basically is that assume that we want to add two 4-bit numbers. So what is the total size of the input? It is 8 bits, right? And the total size of the output maximum could be 5 bits. So what I can have is that I can have a table with 2 raised to power 8 entries, which is like all combinations. And for each combination, I can store the output, right? So let's say it's a 5-bit output. For each combination, I just store the value of the output, whatever it is. So that will give me the sum as well as the carry. Okay. So I can basically take any function. So we have a lot of customized software, extremely sophisticated software these days, that can take any function and basically map it into a set of simple lookup table accesses. Even if we are adding two 64-bit quantities, right? So we are adding two large 64-bit numbers. We can still break it into a large number of smaller computations such that we access these lookup tables. So with lookup tables and flexible logic and flexible interconnects, we can implement anything: addition, subtraction, multiplication, large processors, everything. So a flexible interconnect can be used to connect LUTs and state elements together. So this will provide us with high computational throughput. So note that reconfigurable architectures such as FPGAs. So this method of using PLAs, LUTs, interconnects, and so on. So even flexible interconnects are done with a PLA-like logic only, where let's say we want a packet to go this way. So all that we need to do is we'll have a set of multiplexers over here, and we will then configure it to route all the signals to go that way. So FPGAs also use something called an antifuse. So so that can be seen on literature on FPGAs, right? So basically that is more like a persistent element where once programmed it maintains its state and it ensures that whatever signals come this way get routed that way. But we will not discuss that in great detail. But what we will discuss is that FPGAs are extremely flexible and they have a very large number of logic elements. So you can implement massive parallelism. The only thing is that their clock speed is quite limited, 400 to 600 megahertz. And it's also not the case that one clock cycle achieves a lot of things, right? So even for a simple operation that would take one cycle on an ASIC, it may take multiple cycles on an FPGA. So FPGAs are limited in terms of their frequency, in terms of their area, overheads, everything. So they are fairly, they're extremely used. They're fairly used frequently while creating hardware prototypes. But nowadays they're also used to implement production quality systems because both the efficiency of FPGAs and the software used to program FPGAs that has matured significantly. So for many tasks like DNA sequencing and linear algebra and so on, FPGAs are not bad candidates, but they're quite expensive. So one FPGA is almost as expensive as a state-of-the-art server. So given the fact that ASICs are very good, but again, ASICs are extremely specialized. And furthermore, if I have a small application, I'm not really going to make an ASIC for it. It's too expensive. Fabricating a chip when the market demand is not there or is not that much to justify the huge costs. And given the overheads of FPGAs, particularly for graphics intensive tasks, which is almost everything we do these days, our windowing systems, games, and so on, GPUs were designed. So initially they were handling graphics intensive tasks, like mostly handling the windowing systems of modern operating systems and also games. But later on they were repurposed to run numerical programs and scientific programs, right? So this is how the GPU, the graphics processor unit, became a GPGPU. All right, a general purpose GPU. So what is the need for a GPU? Well, let's do a little bit of math. So consider the display on which I am recording this video. So it has 1920 pixels on one axis and 1080 pixels on the other axis. So it's a high resolution, it's an HD display. The refresh rate, which is the number of frames that I show per second, is 60 frames per second. So this means that roughly 125 million pixels have to be processed per second. If I consider a 3 GHz processor with an IPC of 2, which is medium to high, it will be able to process 6 billion instructions per second, roughly. And so which basically means 48 instructions per pixel. Okay, so this is roughly what we will have to process. Okay, so 48 instructions per pixel, even though it sounds to be a lot, but actually it's not a lot if I look at this high intensity games that we have, all of the effects that we have, all the video that we watch. So nowadays what happens? Nowadays, even if I'm writing a book or making a PowerPoint, I keep on listening to some music on YouTube or keep watching a YouTube video at the corner, right? So then my processor has to do both. It has to run PowerPoint as well as process the sound of a YouTube video and the video of a YouTube video. So typically this much is not enough. So for more high definition and high intensity graphics, we need better platforms for the graphics effects and HD movies. So this is where the need for GPUs comes up. So GPUs are used for many things. So one thing we need to understand before we actually look at GPUs about modern graphics systems. So the modern graphics system, as compared to what things were 30 years ago, where we thought of the screen just as an array of pixels, right? So I'm talking of things 30 years ago. So we thought that the screen has X pixels and Y pixels. So we have XY pixels, and this can be represented as an XY element array. Each element of the array is assigned a color. right? And all that we need to do is we need to compute these arrays and show them. And in monitors of those days that worked at roughly 30 to 50 frames per second, so incidentally, this array is called a frame. So you just have to recompute this array 30, 40, 50 times every second. And most of the time, the array remained constant. There was no change. Only when there was a change, this was updated. But modern graphics is quite different. So in modern graphics, you have to construct the image. So what the user actually writes is a set of rules. That is what the user writes. So these are a set of rules. So let's say there is a character running, in the middle of a city with guns and police cars after him with sirens blazing, as you have in a game. So what the user writes is user defines the objects, defines the interactions between the objects, puts effects such as shadows and illumination and so on. But the final scene has to be constructed from the rules. And furthermore, if it's a small monitor like the monitor of a mobile phone, then of course rectangles will appear smaller, but you'll still see the scene. If let's say move it to a big monitor, we'll still see the scene. So this means that whatever the user does is not really specified in terms of coordinates, but rather in terms of rules. So the user basically says that, look, in this frame, this is the starting and end point of a rectangle. And let's say that, we move it to a bigger monitor, the rectangle will get scaled appropriately. So when this method is used, it's called vector graphics, where, for example, if you're storing a line, we just store its first coordinate and the second coordinate. Now, if you move to another monitor where the line needs to be lengthened, it's very easy to lengthen it because we are not storing each pixel of the line, but rather we are storing the start and the end. So it can be lengthened. So you can have a library to lengthen it and render it. Render it means show it, right? Show it correctly. So we'll discuss about rendering, but rendering basically means creating the graphics object on the screen. So when such a rule-based system is used, as you can see over here, where a rule-based system has been used to create this tree full of fruits. So the image was much smaller, right? Maybe the image was this size, but when I expanded it, it became this size. But it still looks like a good image. It's not blurry. In comparison, I took another image where only the pixels were stored. As opposed to vector, this is called a rasterized image. So the rasterized image, when I actually made it bigger, you can see the blurriness in this image. So this is called raster graphics. So the two paradigms that we have in GPUs particularly is that in the olden days, we mostly had raster graphics because we only cared about arrays of pixels. But after that, very soon, we came to a point where we represent an object as a set of polygons. So you'll see mostly it is triangles, but let's say polygons and shapes of all sizes. And any image is generated by the interaction of these shapes. Here again, there are two generations. The first generation was 2D, the Tom and Jerry kind of cartoons. And the current generation is 3D, where you have these 3D characters in games and movies and so on, right? So that is like 3D. So movies, of course, we don't generate anything, but movies, there is a separate problem that movies come encoded and they need to be decoded by the graphics card. Why encoding and decoding? Because encoding means like heavily compressing a movie and decoding means uncompressing, right? With as little loss of quality as possible. That said and done, most graphics tasks, be it PowerPoint, be it a game, or be it just your windowing system, specify the interaction in terms of objects. And it's the GPU's job to pretty much convert that into a scene which you see on the monitor. Raster graphics is still used in the sense many objects are still specified as arrays of pixels, but that's not all that common. So given the fact that these GPUs were doing so much of geometry, people observe that the GPU could be easily repurposed to create a GPGPU that also does general purpose computation without changing the design of a GPU very much. So if we further look at this, right, if we further look at this need for GPUs slide, you will see that in vector graphics, as we have said, I'm just repeating some things, that the programmer has created a high-level set of objects with shades, textures, characters, worlds, etc. with the rules for interaction. And this vector graphics capability of the GPU was later on used or leveraged to create a GPU, where a GPU continues to do what it was doing, but additionally it can also be repurposed to run absolutely general purpose numerical and scientific codes, right? So this, for example, would be an example of an auto-generated scene from a game where you can see a lot of effects. You can see this complex object over there. You can see the effect of light, shading, illumination. Just look at this point and look at this point. So this point, you can clearly see the effect of the face of the rock pointing towards the sun, and you can see the shade over here. So all of this has been automatically generated after the design was given to the GPU. And you can also see the effect of texture. Just look at the texture of this wall. It gives you a feeling that this is the wall, but this area gives you the feeling it's the sky. So the texture, etc., was all added. So a lot of these things were added. And you will see that if, let's say, I play the same game on a mobile phone, you will pretty much have a very similar visual experience because of the fact that the GPU of the mobile phone can interpret the rules differently as per its screen size. So this is where our GPUs have come to. So now the thinking is that, well, ASICs are very good, but their usage is very limited and they are very expensive to at least create. So there's a very high startup cost. So unless the volume is large, ASICs make no sense. FPGAs again are great for prototyping and maybe a small set of applications. Traditional GPUs, great for graphics. But if, let's say, I can kind of combine all of these three, kind of get the power of traditional GPUs to do graphics, power of ASICs to do general purpose computing, and power of FPGAs in the sense I have a sea of computational units, I'll arrive at the modern general purpose GPU. This is the broad idea. So this can look at games, high intensity graphics, movies, of course, far more powerful than an out of order processor. So we will first focus on the graphics aspect of a GPU, and then we'll look at the general purpose aspect. So first we focus on the graphics aspect. Next, we focus on the general purpose aspect. Okay. So the graphics aspect, what we need is we need something called a shader program, which is a master program which does all the heavy work on objects, vertices, their pixels, right? It looks at transformation, rotation, skewing, and so on. So it applies all the transformations that are needed to images. It applies the effects. So as we have seen in the previous image, it applies the effect of texture, shading, illumination. It does all of that automatically, which also translate to linear algebra operations primarily. But we will discuss how having a general purpose language for these actually translates into something bigger, right? Something much bigger than the scope of GPUs themselves. Let us now show the basic structure of a shader program. So in a shader program, we take in input data, which can be in the form of pixels or vertices. Then we take in these three inputs. So the first input actually comes from a dedicated memory structure known as a texture cache or a texture memory. So this provides all the textures for the image in the image region. Then we have a bunch of read-only data. Think of them as constants for the model. So many GPUs, particularly in the early days, used to have a cache for read-only data. So maybe much of that doesn't exist today, but something of this nature used to be there. It used to be called the constant cache. And then, of course, GPUs regularly communicate with memory. So when we are talking of memory here, it is mostly off-chip memory. So the GPU and the CPU do not share caches. In general, they communicate via the off-chip DRAM memory. And finally, the output is in terms of pixels and vertices. Some of it is stored in the caches inside the GPU. And of course, if more data is generated which is not subsequently used, then it is written to the off-chip memory. So the graphics pipeline of a typical graphics processor, this is the way that it looks, but there are some changes. So one of the stages has changed. So I will describe that later. But the quintessential graphics pipeline that shader programs use, it is a dedicated graphics pipeline that has these four stages. The first is the Vertex Processor, then the Rasterizer, the Fragment Processor, and the Pixel Engine. So what the programmer does is that she specifies a scene in terms of the basic broad objects and the interaction between the objects, the light sources, illumination, shading, the normal vectors of the surfaces, and so on. The rest is automatically computed in hardware and in software. So there are dedicated programming language APIs that allow you to write all of this code. And a lot of it at runtime is converted into PTX code and what we shall see SAS code. So we'll discuss that later, but essentially native code for the GPU. So there are two very common APIs, application programming interfaces, that are used. Windows systems often use DirectX, and OpenGL is quite platform independent. The GPU programs are typically written in two parts. There is a part that runs on a normal CPU, and there is a part that runs on the GPU. So this is compiled in a GPU specific ISA, right? So basically you can think of it as a fat binary. A fat binary basically contains code of different instruction sets. So the program binary, as we discussed, is fat in the sense that it contains both CPU code as well as GPU code. So NVIDIA programs are first compiled to a virtual ISA. So we will discuss in detail in later lectures what is exactly the need for a virtual ISA. But that's what NVIDIA programs are compiled to. And the virtual ISA is called PTX, or Portable Thread Execution. That is a virtual ISA. And at runtime, the PTX virtual ISA is actually compiled to the actual ISA. So this is something like Java, where let's say if you take the code of a program, you first compile it to PTX and then you distribute that. So this ensures that nobody is seeing your code remains safe, your intellectual property remains safe, and you assume a virtual machine and design an ISA for it and distribute it. But real time, a lot of optimizations need to be done. And these optimizations are nicely captured by the compiler for that specific GPU. So that specific GPU at runtime, it is dynamically compiled to SAS or shader assembly. So the Vertex processor, this is the way that it looks, which is the first stage. So recall that there are four stages in the pipeline. So we typically decompose a 3D surface into a set of triangles because it is very easy to work with triangles. And triangles also have some inherent advantages, right, which other representations don't have. The most important being that all the vertices are on the same plane. So it's very easy to specify the plane of a triangle and its normal vector. We can then compute effects such as reflection very easily. And also there is a lot of literature on processing triangles, and most triangle operations ultimately degenerate into matrix operations. We can perform ray tracing, which is trace the path of light rays, see how they interact with surfaces. So that will give you effects of illumination and reflection. Finally, we can add color and texture to a surface. We can move, rotate, and scale the objects as is required, and also calculate the depth of the triangle, which is the depth of the object in the image as measured from the eye. So with that, what we can do is that things that are far away will appear to look slightly different, And also they'll be occluded or hidden by nearby objects. So this occlusion is important, of which object hides the other object, right? And so much of this is computed here, but it's also computed later. So the vertex processor you can think about as the stage that performs all the geometric operations on the shapes. So this heavily uses linear algebra. And previously this was using custom hardware. Now the vertex processor's code is basically mapped to generic hardware. And on generic hardware, it just translates to tons and tons of linear algebra. So nowadays, the Vertex processor has been replaced by the Polymorph engine. So the Polymorph engine itself is pipelined. It has a 5-stage pipeline. So if you think about it, there is a pipeline within a pipeline stage. So the Polymorph engine has 5 stages: vertex fetch, tessellation, viewport transformation, attributes setup, and stream output. So in modern GPUs, they don't have the Vertex processor again. So I must underscore the fact that we are mostly talking about NVIDIA family of GPUs over here. We are not talking about other GPUs at the moment. So in the Vertex fetch stage, what happens is we convert local object coordinates to world coordinates. So normally what happens is that in the programs, in the shader programs that users write in OpenGL, for example, they specify local coordinates, but all the objects are not in the same coordinate system. So when all of them are in the same coordinate system, this is referred to as world coordinates, where you use the same axis, same 3D axis, X, Y, Z for all the objects. And then the next part of this vertex fetch stage is to also fetch the vertices and then do geometric operations on top of them. So this is where we simulate the motion of limbs, for example, in lifelike characters, move objects, you're shooting a bullet, the movement of the bullet. And we also, along with pre-programmed motion, we also look at other visual effects such as illumination, shading, and so on. So we have a process here known as the hull shader. So what this does is that, let's say it takes a large polygon. So a large polygon may be something like this, right? It divides this into a smaller set of polygons, right? Could be triangles, and could be triangles, maybe triangles, may not be triangles, doesn't matter. But it is just that objects which are closer to the viewpoint, which means closer to the eye, they have a higher granularity. In a sense, the resolution is better, and objects that are far away from the viewpoint, they have a lower granularity. This roughly corresponds to the way that we view objects. That objects that are close to us, close to our eye, we tend to see them better. So if, let's say, this is the eye, and let's say, an object that is close by, we tend to see it much better, as opposed to even a large object that is far away, we don't see that much of detail in it. So this is also coming in over here. So then we have tessellation. Tessellation basically means once we have created the polygons, once you have manipulated them to some extent, right? We break them down into a set of smaller objects, or which are triangles and line segments. So we have already discussed the advantages of triangles. The advantages of triangles are twofold. First is a triangle lies on a single plane, and second, there are lots and lots of algorithms. There is a lot of research in computer graphics to work on triangles. The third stage is known as viewport transformation. See, the total scene is the window. If I create a large scene, right? So it's a large scene with a lot of objects, characters, and so on. All of it will not fit in my screen. So what will fit in my screen is a subset of this that I choose, known as a viewport. So what this stage will do is this will kind of get rid of all the objects or parts of the objects that are over here and only focus on the viewport, right? So the first stage was vertex fetching. We will primarily fetch the vertex, divide it into polygons, smaller polygons, do some geometric operations. Then tessellate, which is to divide it into triangles such that we can do more operations on it. Then we focus on the viewport. the part of the scene that is visible. Then this is a very important step because this step has further ramifications down the pipeline. In the sense, other stages which are later on in the pipeline, they tend to read data from this stage. So here what we do is we compute the depth of each object. And so let's say if there is a complex object like a stone, so we find out how far it is from the eye, okay, the distance. We annotate its front face. So if this is the front face, so basically the part that is visible, that part is annotated, right? So this part is annotated. And then if let's say there is a small light source over here, then we look at different rays of light and see the way that they interact with the surface. And given the fact that different parts of the surface have different normal vectors, there'll be different degrees of reflection and scattering of light. So all of that is computed in parallel, of course. So basically the list of triangles, some degree of illumination information, some degree of distance information, right? Illumination and distance primarily, distance from the eye, right? A hypothetical eye, of course, and the illumination of the front face. This information, which is basically a huge list of triangles, this is written to memory, such that it can be passed to the next stage. So in some cases, it is written to the cache and it's kind of internally pipelined to the next stage. In some cases, there is a need to actually write it to main memory. The next process, so basically we finished the first stage of the big pipeline. So in the first stage, we looked at the Vertex processor, which has been replaced nowadays, as I said, with the Polymorph engine. So given a set of triangles, we convert the set of triangles into a set of fragments. So a fragment basically is a set of pixels. And so instead of looking at a triangle as a geometrical thing, we do the same thing. But in this case, since you are aware of the display, we look at each pixel within the triangle. So this triangle then becomes a fragment. We here again optionally can compute the color and visibility of each fragment. And given the fact that rasterization, well, of course, is required, but it does not involve a lot of geometric operations, it is hard to derive any general purpose value out of a piece of hardware that does rasterization, quite unlike the Polymorph Engine / Vertex processor. Consequently, there is a dedicated hardware unit even in modern GPUs that performs rasterization. This is known as the rasterizer hardware unit. Okay, so this does the process of rasterization quite well, in fact. So next we come to the third stage, which is known as a fragment processor. So what does the fragment processor take from the previous stage, which is the rasterizer, is basically a set of triangles in kind of pixel format. Okay, but the triangles are not fully developed. So there is a need to develop the triangles, in the sense map it to the final scene. So to develop the triangles, what we need to do is that we need to find the color of the fragment, right, or color of the pixels within the fragment. The information that we have up till now is just the color of the three vertices of the triangle. We don't really have the information of the internals of the triangle, right? So in this case, the broad idea is like this, that we find the colors of here and we somehow try to interpolate, try to find out the colors from here just by applying a function on these three colors and of course the dimensions of the triangle. Then we add a texture over here, right? So we also superimpose a texture over here. For example, if this is wood, we'll superimpose wood. If it is brick, we'll put in brick. And finally, fog computation, which is something similar to what I had said before, that objects that are close by to the eye look slightly differently. So if let's say this is the eye, object that is close by looks differently in the sense the resolution is higher, we see brighter colors. Objects that are far away also appear to be slightly darker. But then this also depends on the light sources. So accommodating these effects is known as fog computation. So we will discuss this. So what are the three sub-stages here in the fragment processor? Interpolation, which is finding the color within the triangle, texture mapping, and fog computation. So for interpolation, there are two shading stages. So it's called Gouraud shading and Phong shading. Gouraud shading is simpler, Phong shading is more difficult. The idea over here is to find the colors of the pixels within the triangle. So here we assume that the triangle is a flat surface. So this is a quintessential assumption that a triangle lies on a plane, it's a flat surface. We take into account all the sources of ambient light. Okay, so basically wherever there is light, we take into account all the sources, including reflections from other triangles, right? Take all of that into account. All the rays are kind of, let's say, hitting this triangle, right? The triangle has a normal vector oriented along some axis. So if we compute the dot products, we'll find out the light that is hitting the triangle, the color of the light, of course, that is hitting the triangle. We need to take into account the absorptivity and the reflectivity and the transmissivity of the surface, in the sense that this can be a translucent object as well. But let's leave translucency for the time being. So if we look at the reflectivity of the surface, then what we can do is we can take this into account. And we can also look at the colors of the vertices over here, all three. Use a complex function, which is of course easily computable in hardware, to find the colors of all the pixels within the triangle. Alright, so this is known as Gouraud shading. The other approach is known as Phong shading, which is more complicated, where we assume that the triangle need not be a plane, need not necessarily be a plane. It can be a smoothly varying surface. Okay, so it could be a surface like this. So let me just draw a bigger version. It just could be a surface like this. Okay, and this will have a very complex model of reflectivity, which will of course be far more time consuming. But this may be able to model a smooth surface quite well. So we are of course breaking the assumption that a triangle lies on a single plane, but this may be able to model the surface of a kind of an complex sloping object much better, right? So this was all about Gouraud shading and Phong shading. Both fall in the class of interpolation algorithms for pixels within the triangle. Next, coming to textures, as you can see, there is a brick texture here, dirt, wood, and so on. So we are applying a texture to each fragment. Most GPUs will have a dedicated cache to store texture information. And the last is fog computation. So fog, think of it as distance fog. So if you look at the pixels that are close by, you see a better granularity. They appear clearer, right? But look at the distances far away. They appear blurred, right? So there is lesser of a granularity. Also see the lines, even though the railway line is parallel, don't you see at the end it appears to kind of converge? It does, right? So these effects that provide the perception of distance are known as distance fog. And since the Vertex processor is already giving us this information about which object lies where, in the sense that from the eye, if I were to measure the distance, then which object is how far, this information can be used here to render the scene. Render means create the scene from the rules. So I said the effect of distance is clearly seen. So this is known as fog computation, which is the third substage in this stage. Finally, we come to the last stage of the traditional GPU pipeline. It is known as the pixel engine. So the pixel engine by and large does two things. It does depth and color buffering. So different fragments have different depths. Okay, so call them as, it's called the Z depth or the Z depth. So let's call it the Z depth. Based on the Z depth, we compute the visibility of the pixels, because what could happen is we could have two objects one object could be hiding a part of the other object. So this is known as occlusion. So these effects of occlusion, where one object is hiding a part of the other object, this needs to be computed. How will it be computed? Well, the way that it will be computed is like this, that we know the coordinates, the end coordinates of all the objects. So we know where they stand with respect to the eye. We know their z depths. So we just compute the visibility of each of the fragments, right? Each of the pixels. If you want to go one level lower, but typically the fragment level is fine. So then we can deliberately hide or occlude parts of the objects. Furthermore, we can look at translucency. So we had discussed translucency earlier also. So given that we had promised to come back to translucency, here it is. So the pixel color value is represented using 32 bits normally. There is a RGB channel, right? RGB is red, green and blue. So we have 8 bits each to indicate the intensity of the color for RG and B, and alpha is the degree of transparency, right? So one end is fully transparent and other end is fully opaque, and anything in between is translucent. So these values are also computed, and the translucency effects are taken care of over here in the pixel engine, where we display the translucent engines in this translucent objects correctly. And finally, once the entire scene has been created, it is sent to the display device, whatever it may be, the monitor or large screen display projector, whatever it may be. So by early 2004, high-end processors were approaching a peak throughput of around 20 gigaflops. But even those days, GPUs were exceeding 50 gigaflops. It is just that GPUs were doing their own thing. They were doing graphics computations. And there was no way to repurpose or use a GPU to do general purpose computations. But the processing power of a GPU was increasing by leaps and bounds. So it became 170 gigaflops in just within 1 year. And then just kept on increasing, right? So it reached a teraflop very soon. So now, evil processor designers and programmers laid their eyes on GPUs. So they thought it's a good idea to repurpose the GPU's resources, in the sense that a large part of the computation that you have just seen involves linear algebra. Other than the rasterizer, to some extent, most of it is generic linear algebra. And if that is being done for a graphical scene, it can be done for other high performance and scientific workloads as well. So what we can do is that we can have a more generic design of a GPU, where let's say the programmer writes in a certain layer, call this the programmer layer. Then there is a layer of software which provides a lot of APIs and libraries and resources to kind of convert it to another lower layer, and again a bunch of other layers. We have already discussed PTX, and then it's a virtual instruction set, and SAS as shader assembly. So with this set of layers, a simple graphical operation can sort of be mapped to a large number of linear algebra and numerical operations. And if a graphical program can be done, we can take any other program and just map it to PTX. PTX should ideally not care. And this can be even a general purpose program. So this is how the idea of a general purpose GPU was born, where the GPU processes scenes, that's fine. And then we can repurpose the hardware. So before repurposing the hardware, an initial solution was to repurpose the software. In the sense, what we do is that instead of directly making the hardware generic, what people initially did is that they took linear algebra calculations for other problems, mapped them to scenes, allowed the GPU to process the scenes, and extracted the results from the computed scene. Which, if you think about it, is a really indirect way of doing things. It's much better to repurpose the hardware. That is exactly what they did. They designed more flexible GPUs instead of repurposing the software, right? Make the hardware generic such that it can do graphics oriented tasks as well as non graphics oriented tasks quite well. So now we have finished the first part, which is discussing traditional GPUs, ASICs and FPGAs. And what we have realized is that traditional GPUs have a lot of power. It is just that initially it was not realized, but later on, once it was realized, a more generic substrate was created. So the next two sections will talk about the software aspect, which is programming the GPUs, and then the design aspect of how do we exactly design them. So this lecture, which is the first part, will end over here, and the second part will be there in the next lecture.